Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome to the lecture today, and we would like to start the new topic on strengthening mechanisms in crystalline materials. So when you talk about strengthening mechanisms, if you look back what all the background that is required to get the grip on this subject is, like, again, as I mentioned in the earlier sections, some idea about crystallography and dislocations and stress fields and so on. Okay, so when you say strengthening mechanisms, you are going to strengthen. We are going to talk about strengthening the crystalline lattice, right? So there are several ways by which you can do this process. So we would like to see one by one, and before we really getting into this topic, suppose if you consider the fundamental ideas that is required to grasp before we get into this is like stress fields in the lattice. Suppose if you talk about solid solution strengthening, and then the stress field around the uh, solid solutions, right? That is one primary concern. The other thing is we just talked about a lot as a dislocation, and the stress field and strain field around the dislocation also has a important role to play. In fact, it has got a primary role to play, because we are going to talk about dislocation mediated activities, or like deformation. We talked about dislocation mediated plasticity. Here also, when we involve plastic deformation to incorporate the strength, then again same idea will bring in. But then if you talk about solid solution strengthening, that is a first one to look at it. Then you talk about two things as an addition of solid solution. I mean, addition of foreign atom to the matrix. Then what all the changes it brings in, and what kind of stress field it's surrounding the solute atom with respect to the solvent atom or solvent matrix. So these are all the concerns. So we will recollect what we have already seen in this dislocation. We have this idea about what kind of stress field around the edge dislocation. So we have seen that it is quite complicated, but we have the idea about the above extra plane. The state of stress is hydrostatic compression, and below it is hydrostatic tension. And along this, y-axis, it is completely hydrostatic. There is no shear stresses in this. But on the other hand, if you look at the x-axis, there is no hydrostatic stresses, but only shear stresses in both sides. So these are all we have already seen. And we also looked at the stress field in this form, if you recall, which clearly demonstrates whether it is attraction or repulsion in the fourth quadrant with respect to the coordinates of x and y. Okay, so this is very important to recollect, and depending upon this, what kind of stress field is there in this dislocations, and also what kind of stress fields exist in the solute environment, the interaction energy is going to be decided. So the whole strengthening mechanism, solid solution strengthening mechanisms, revolves around these two fundamental aspects. To summarize, what is the we have idea we have the, as far as the shear stresses and the normal stresses around these dislocations are concerned, we know that the screw dislocation is primarily associated with the shear stresses, but the edge dislocation has got both shear and normal stresses. In fact, you have one shear stress component and then 3 normal components in edge dislocations, and they are also hydrostatic in nature. And as far as screw dislocation is concerned, it is mostly shear component. The other important idea we have to remember is, at the moment we talk about the shear components, it is a distortion. It is related to distortion of the bond. But the hydrostatic or normal stresses, as we talk about, it is also related to dilation. So you have to remember these two aspects. So in the case of screw dislocations, we can talk about only a distortion. That is a distortion energy associated with this. On the other hand, if you go to edge dislocation, you have both dilation as well as distortion. So it is with this background, if you approach the solid solution strengthening, then it is easy to understand and then move forward. Okay. So the first and foremost topic is general description of strengthening. We will first look at general strengthening aspects. The strength of a crystalline material is increased by obstacles that restrict dislocation motion within it. So to stop the dislocation motion, we have seen several forms. In fact, we looked at even friction stress that is exist in the lattice. Okay, a perfect lattice called Pearl stress. We have seen that. So that also will have influence here. But here we are talking about an external obstacle and a foreign object which is going to stop the dislocation motion in the parent matrix. This is what we are talking about. So let us look at the schematic here. What is shown here? What you are seeing here is a matrix where you have all the dispersion kind of obstacle. We are not defining this, and this is the dislocation motion direction. So, and what you are seeing is the dislocation line which is trying to pass through this obstacle. And then what you are seeing here is these particles are trying to stop. That's why it is the dislocation line is getting bent over here, and the angle between these two line tension we call it, and it is phi c, and then the distance between the two obstacle is L prime. Okay, so each particle in the matrix is considered as a obstacle here. So what we are really talking about is the stress required to overcome the obstacles depends on the effective spacing L prime between the obstacles along the dislocation line and the angle phi z to which the dislocation bends before it breaks through them. It's a kind of extrusion between these two obstacles. These dislocation line is are trying to come out or extrude themselves between these two obstacles. That is what we are trying to show. The stress required to produce continued motion of the dislocation through the obstacle array is the macroscopic yield or flow stress. So this is one way of a holistic view. What is that we talk about as a macroscopic yield or a flow stress, which is nothing but the stress required to produce a continued motion of dislocation through the obstacle array of obstacles. It could be any second phase particle, or it could be a defect, it could be boundary, etc., etc. Okay, so this is that is the idea. Now we can have these obstacles in the different forms. the obstacle strength essentially determines the flow stress. So we are talking about here the second phase particle in the matrix, but then whether the second phase particle is hard or soft enough as compared to matrix. There is always a relative comparison of the hard or soft nature of the second phase particle with respect to the matrix. That is why the strength, the term strength comes into picture. So strong obstacles resist dislocation penetration. So now we are talking about the other event, like the dislocation not only gets stopped, but it also will stop them to penetrate the particles or penetrate the obstacles. Okay. So this is reflected by phi c approaching 0. So what is phi c approaching 0? You can see that these dislocation lines, they are all trying to extrude between these obstacle particles. Then the moment it is, the penetration is completely resisted, then you see that the phi c is almost becoming 0. So that is the idea. So the phi c is 0. The spacing between obstacles is also important. So in the strengthening mechanisms, especially of this type, that obstacles, dispersion strengthening, or second phase particle in the matrix, the spacing between the obstacles is a quite important parameter. If you look at this image, this is also showing some second phase particle in the matrix, but the situation here is quite different. What is the different here? Here the dislocation line is not curved like this. That means the obstacles are pinning this and then resisting the motion, and then the dislocation line is trying to extrude between them. But here the dislocation line is simply travel through or penetrate through, cut through all this. Okay, so that's the difference. For strong obstacles, the effective spacing is the mean spacing between the obstacles on the slip plane, L. If, on the other hand, the obstacles are weak, phi c is very large. So this is a difference. So we are talking about phi c approaching 0 here, but here it is, the line is just simply going to move like this. So there is no, significant influence of phi c here. Phi c is almost equal to 180 degree. So the angle between this, the dislocation line and the obstacle, will be almost 180 degree. That means the dislocation line is much straighter for the situation of weak obstacles. So this is what it is, penetration means. Okay, the dislocation is cutting through or penetrating through. As a corollary, the effective obstacle spacing L prime is much greater than L. So very important point. So here, if you, in the previous case, when the obstacle is completely resisting the dislocation line to penetrate, then the effective spacing is different, that is L here. But on here it is not like that. The dislocation is simply going to cut through. For example, if you take this particular line, and what you are seeing here is one particle is sitting here, one particle is sitting here, which is measured as L prime. But at the same time, you can also see the other particle sitting here, other particle. So it is an average of these particles distances that is going to be L prime. Okay, not just the distance between the two particles. So there is a difference between a hard and weak obstacles for the dislocation motion. This is very important. Okay, the stress required to overcome the obstacles depends on the effective spacing L prime between the obstacles along the dislocation line and the angle phi c to which the dislocation bends before it breaks through them. Okay, this is important. So the stress required to bend the dislocation to the angle phi c is calculated in a manner analogous to that used to determine the stress required to operate Frank-Reed source. You see, now we know what is Frank-Reed source. We have already seen this. And how did we calculate the stress required to generate the dislocation multiplication? So you have to recall that. So we introduced a term called line tension, right? So an appropriate line tension balance, taking the dislocation line tension as GB square by 2. This is what we have seen. If you go back and see, this is what we have shown already. At the critical angle shows that the necessary shear stress for the continued dislocation motion is tau approximately equal to GB divided by L prime times cos phi c by 2. Okay, where L prime is the effective spacing. See, what you have to remember now, any expression we are showing in this, at least these domains, they are all semi-qualitative. Okay, it is semi-quantitative, not qualitative. Qualitative, it's mostly qualitative, but when you try to do a quantitative, it is not 100%. It is a semi-quantitative expressions mostly, because the complexity complexity of the problem, you are seeing that, right? How complex it is. So most of the expressions what you are going to see in this particular section is semi-qualitative in nature. Okay. As noted, for strong obstacles, phi c is equal to 0 and L prime is L. Thus, the maximum strength associated with a given obstacle array is tau max is equal to GB by L. With a decreasing obstacle strength, phi c increases. Okay, that means the particles become weak. This is what you have to understand. An overestimate of the operative stress for a strong obstacles is obtained when L prime is equal to L is tau for a strong obstacles is equal to GB by L times cos phi c by 2. Friedel has considered the case of weak obstacles and has shown that as phi c tends to pi, L prime becomes approximately equal to L by cos phi c by 2 whole to the power half. Thus, the approximate strength provided by the weak obstacle is given by tau weak obstacle is equal to GB by L times cos phi c by 2 whole to the power 3 by 2. Okay. So these two expressions give some idea about the stress required to surpass the obstacle, whether it is when it is weak or strong, or you can say hard or soft. Okay, some semi-quantitative idea. So the next mechanisms which we are going to talk about is work hardening. The term is quite familiar to us now. We have already looked at some of the crucial mechanisms which is involved in plastic deformation of single crystals. So we are talking about polycrystal now. So what is work hardening? So dislocation interactions during easy glide of a single crystal plasticity provide an example of soft obstacles. Okay, in a single crystal deformation, we talked about quite a lot of dislocation interaction and reactions. So they are all considered soft obstacles. Okay. So in stage 1 hardening can be considered to rise from the stress field interaction of dislocations moving on a parallel slip planes. And dislocation intersections produce hard obstacles. So this also we have seen. What kind of intersections will produce hard obstacles? Then one example is jog. Okay, jog or vacancies and so on. They are all hard obstacles. This is all we have seen. This is manifested by the high work hardening rates of our polycrystals and the single crystals during stage 2 deformation. So this also we know. As we move from stage 1 to stage 2 to stage 3, the obstacle generated even within the dislocation reactions, they are quite high. Okay. The jogs are hard obstacles and they are circumvented by dislocation extrusion between them in a manner analogous to operation of the Franklin source. So Frank-Reed source also, how it produces, we have seen that the dislocation line is getting extruded between two obstacles, and then they join together, and then they form a loop, and then it continues, something like that. Okay. The flow stress can be described in terms of approximate equation mentioned above. That is, assuming all the dislocation relationship, that is L square times rho is equal to constant. The shear flow stress is then given by tau is equal to tau naught plus alpha GB times into rho to the power half. Okay, so this is one important flow stress equation in terms of dislocation density. Okay, we know what is tau naught. Tau naught is frictional stress. We have already seen that. So where tau naught is the intrinsic strength of a material having dislocation density low enough so that the dislocation interactions are inconsequential, and the empirical constant alpha represents the correction factor necessitated by the approximate applicability of shear stress equation. Okay. For a BCC metal, alpha is 0.4, and for an FCC metal, alpha is 0.2. So this particular hardening mechanism is purely based on dislocation interactions. Okay. Since we have already discussed quite a bit about dislocation interactions and also plasticity of single crystal and polycrystals a little bit, so the concept here is the same. So that's why I just want to briefly mention here. And this equation gives an idea how the dislocation density controls the shear flow stress. Okay. The next strengthening mechanisms which is important is boundary strengthening. See, we are now talking about obstacles for the dislocation motion. Okay. And then initially we said that the obstacle could be dislocation itself, or it could be a second phase particle. And then we see that we have also seen that whether second phase particle can be hard or soft. Okay. But now we are talking about a boundary. The boundary is a very strong obstacle for a dislocation motion. Okay. So we are going to see that. Grain boundaries are particularly effective obstacles to dislocation motion. Crystallographic factors do not permit the passage of a dislocation from one grain to adjacent one through a grain boundary. Okay, it is not easy because you know that in a polycrystalline material, each grain is oriented in a particular manner. They are not the same, and that is why we have the boundary compatibility issue and all we have seen while talking about plastic deformation, right? The stress concentration due to the dislocation pileup in an active grain increases with number of dislocation that come up against the impenetrable boundary. Okay. So let us read this sentence again, very important. The stress concentration due to the dislocation pileup. We know the word dislocation pileup. What does it mean? Okay, dislocation get piled up against the one obstacle. We have also seen in this term how the dislocation get piled up against the obstacle in the dislocation mechanics, right? So this can happen within the grain. It's an active grain. What do you mean by active grain? Active grain means this is the one grain which is favorably oriented. That means this grain has got maximum shift factor and orientations are favorable and the slip activity is going on, the deformation proceeds. That's what it means, active grain. Increases with the number of dislocation that come up against the impenetrable boundary. Impenetrable boundary, that means because the next to grain need not be favorably oriented, or it may not be experiencing the similar critical resolved shear stress to take over or continue the plastic deformation which is active in one X or Y grain, it can simply pass through. There is a problem. There is a boundary. That's why it's called impenetrable. That means the dislocations cannot simply pass through. It will get stopped. Okay. So that's what it is shown in the schematic. You can see that the grain 1 with the diameter D, and imagine that this dislocation pileup is happening in this grain 1. That means the slip systems in this grain are active, or multiple slips are happening, whatever it is. At least you can see that the dislocation is getting piled up against this boundary. And this is the second grain. And then you have some source is there where the there is a potential for the dislocation multiplication, which is there from the boundary with the distance r. Okay, but then to activate this dislocation multiplication in this stress has to assist the dislocation pile up from here, and then boundary stress concentration which is built up here will try to assist that or try to activate that source. So that is something we are trying to see. So the micro yielding in grain 1. What is micro yielding? That means though it is a polycrystalline deformation, since only selective grains are going to start the plastic deformation because of its orientation and slip factor and so on. So the yielding will start locally here. That is why it is called micro yielding. So the first yielding is going to take place in this grain, and the other grains are not going to yield similar extent where it is favorably oriented. That's why it is called micro yielding in a grain. Favorably oriented for slip may proceed macroscopic yielding. So this will all, this is just one grain we have shown in a polycrystalline. So like that, several grains may have similar situation, but some other rest all the grains may not have a similar situation to start with. Okay. So the macroscopic flow requires dislocation activity in all grains. Okay, and this may be induced by the internal stress caused by the dislocation pileup at the boundary in grain 1. So now we are to have the continuous, plastic flow. The cooperative, displacement of all the boundary is mandatory. That's what we are saying. If that is not going to happen, it is going to create a void or overlap and so on. This we have already seen. We have a sufficient background to discuss that kind of a concept. So this is what is shown here. So the stress concentration which is generated because of this pileup against the boundary will induce the the plastic deformation in the other grain like this. This stress may cause a dislocation emission from the boundary and may activate a dislocation source at a point R in a grain 2. So this boundary is going to activate this source because of the stress concentration against it. The magnitude of stress concentration depends on the number of dislocations in the pileup and increases with the grain diameter D. So this is quite obvious, right? So the more the grain diameter, the more the dislocation more number of dislocation will join the pileup, and the stresses will be more. So this process can be described semi-quantitatively. So like I said, all this mathematical treatment in this mechanisms will be semi-quantitative in nature. Suppose tau star is the stress required to activate dislocation motion in the unfavorably oriented grain, and these dislocations are located at a distance r from the boundary. The stress concentration due to the dislocation pileup in an active grain increases with the number of dislocations that come up against the impenetrable boundary. In turn, this number increases as the mean slip distance, that is the grain size D in an active grain increases. analysis shows that the dislocation activation in the second grain occurs when tau applied minus tau naught times d by 4r to the power half, which is equal to tau star. So what is tau star? Tau star is stress required to activate dislocation motion in the unfavorably oriented grain. That should be equivalent to this. What are these parameters? In the equation, tau app is the applied shear stress at which the activation occurs, and tau naught is the intrinsic stress assisting dislocation motion in deforming grain. The parameter d by 4r to the power half represents the stress concentration arising from the pileup. Very important. So we have been looking at the shear stress which is required to move the dislocation and obstacles and so on. Okay, so what is the pileup effect? The pileup effect is this. That's why the parameter comes. D by 4r to the power half represents the stress concentration arising from the pileup, and this increases with number of dislocation in it with the D. So this factor parameter is going to contribute as the grain size is going to increase. That is how we should look at it. So if you rearrange these expressions, which allows the applied shear stress to be expressed in terms of grain diameter. So tau app is equal to tau naught plus 2 tau star r to the power half d to the power minus half can be written like tau naught plus ky prime into d to the power minus half. If you write in terms of yield strength, tensile yield strength, above equation analog is tau app becomes sigma y and tau naught becomes sigma naught plus ky prime becomes ky and d to the power half remains. So what is this equation? This equation is quite popular. This equation is known as Hall-Petch equation, and its prediction that the yield strength of a polycrystal increases linearly with d to the power half has been substantiated in several materials. So in the boundary strengthening mechanisms, Hall-Petch equation clearly demonstrated that the yield strength can have a profound influence on the grain size. Okay. So as the grain size decreases, yield strength will be increased. That is what this equation shows. Okay. We will come back to this equation in a much later stage. Okay, when we talk about deformation and of polycrystals, or when you do a mechanical testing, what happens? We will have few more parameters. You can modify this, and then we can discuss about what is the significance of K and what is the significance of D and so on. And you can just imagine in this equation, suppose if D is 0, what happens? It becomes sigma y is equal to sigma naught. That means it becomes single crystal. Okay, it becomes single crystal deformation. But the moment it becomes, you are bringing in a boundary, then you have the influencing parameter called K here that will have give the much more narrative about how the grain size influences, which is a characteristic of individual systems.